Hello, and welcome to Sequences Part 2. Welcome back. I believe that cute little boy is where we left off last time. So, last time we did arithmetic sequences. This time we are going to be talking about trick sequences. Oh boy. So, how they're different. Instead of arithmetic sequences where you add or subtract the same number each time, geometric sequences are multiply or divide each time. And that number that you're multiplying or dividing by each time is called the common ratio. We can find that by dividing consecutive terms. Wait a second, Mr. Barnett, you've been talking all this time. Shouldn't I be taking notes? The answer is yes. You can abbreviate, but take notes. Write down what you think is important. Geometric sequences relate to exponential functions. Alright? Where the x values are like recording the places of the y values, meaning like the x values are generally going to be the first term in the sequence, second term in the sequence, third term in the sequence, and so forth. And of course we're going to use explicit and recursive rules, just like we did with arithmetic sequences. Okay, got a lot of stuff going on here, but start off with just this sequence. You notice that it gets bigger, goes from 2 to 6 to 18 to 54. And I think you guys would very easily tell me that each time it multiplies by 3. That's good observation. What we're going to do with that is once we have this, we can plug it into a table, noting the first, second, third, fourth, and fifth term, and plug them in there. And to answer this question, what's the common ratio? You guys already found that. Each time we multiply by 3, so the common ratio is 3. Notice that if you were dividing, the common ratio would be 1/3, for instance, if you divide by 3 each time. What's the first term? So we already have that using only positive values for x. And what we mean is we're not trying to find the y-intercept in this case like the 0, like we did in the first one. We're just looking for the first term. And we have that. First term in this case is 2. And that's really all you need to write an equation given the points of a geometric sequence. The reason why is because if you remember the standard form from exponential functions, where we had ab to the x power, we can kind of put them together to get our equation. So we have y, or f of x, is equal to this 2 number right there. That is the first term. Okay, we used it before as the y-intercept. Sort of similar here. This one's talking about the first term, not the 0 term, because of this. Instead of that just being 3, the common ratio to the x power, it's 3 to the x minus 1, which is why we don't want to look at the 0 term, because if we do 0 minus 1, we're not looking at positive values, and of course 0 is not positive either. So we're sticking, the kind of general form you have here is the y, or f of x, is equal to the first term times the common ratio to the power of x minus 1. Okay, and of course that's your explicit rule. Now if we were to write that as a recursive rule, remember we need to know something about the first term, so f sub 1 is equal to 2, and we get that from here. And we know that each term in general is 3 times, that's where this is, the term before it. And this n minus 1 business, what that means is if n is the term we're talking about, n minus 1 is the term before it. So what this tells you is you take every term, multiply it by 3, the term before it by 3, and your first term is 2. But there's also this business here of n is greater than or equal to 2. The reason for that, if you take 2 here, subtract 1, you get 1, and then it comes back to this stuff. So it all checks out. We want to make sure that we're only going the terms for n is greater than 2, meaning the first term, second term, third term, fourth term, once you've subtracted 1 here or here. Okay, so maybe pause, discuss with your partner, see if any of this makes sense, where all these things coming from. You can always rewind, listen to it again. Okay, let's move on. Okay, what if you have two terms of a geometric sequence, but they are not sequential? Now, all the examples in the books I've seen, they're never like 10 terms away. That'd be really difficult to do. But fifth term and seventh term. Oh goody, we have fractions. Fifth term is 1/60th. Seventh term is 1/15th. What's the explicit rule? Well, you do know with a geometric sequence that you're multiplying something by each term. Seventh term is equal to whatever the sixth term is times whatever our common ratio is. And the sixth term is the fifth term times the common ratio, just by definition of what a geometric sequence is. The term before it, you multiply by the common ratio to get the next term. So therefore, if we apply this logic and this logic, that means the seventh term is equal to the fifth term times the common ratio times the common ratio, or common ratio squared. So let's think about that. If we had a list of 1, 2, 3, 4, and so forth, if you were trying to find this second term to get from the second term to the fourth term, it would be this number right here times the common ratio to get this new number, and then times the common ratio again to get this number. Well, that's what this means. So times the common ratio times the common ratio. That's going to be important for this part of this problem. Okay, and all that information is up there smaller. So if let's see, this is the seventh term is 1/15th, fifth term is 1/60th, times the common ratio, which we're going to call x, times another common ratio again. That simplifies. X times x is x squared. And then if we have the equation 1/15th is equal to 1/60th x squared, to get this x squared by itself, we are going to divide both sides by 1/60th. In case you forgot how to divide fractions, you can do the keep change flip method. I'm going to do the toilet bowl method because it looks like a toilet seat method. So because it looks like a toilet seat, and we're going to do 60 times 1 is 60. That's your numerator. 1 times 15 is 15, and that simplifies to 60 over 15 is 4. So that's how we get this. So then you get 4 is equal to x squared. Take the square root of both sides. Obviously, we don't need to worry about the negative roots in this case because that wouldn't make sense in this problem. And we get x is equal to 2. So the common ratio in this case is 2. That's what we were trying to find, the common ratio. That's part of it, but not all of it. Okay, so now we have a common ratio of 2. We just need to find the first term, or what is also known as a sub 1. So if you have any term is equal to a sub 1 times 2, that common ratio times n minus 1. Well, let's just plug in some stuff. So we have the fifth term is 1/60. We could have done the same thing with the seventh term and 1/15th, but I mean, 1/60 is equal to the fifth term. So instead of n there, we're going to put in 5. And since it's subtracting 1, 5 minus 1 is 4. And we can simplify 2 to the fourth power to get 16. If we're trying to figure out the first term, this would just be 1/60th is equal to the first term times 16th. We're going to divide by 16 on both sides, And so we have 1 over 60th divided by 16, or we can call it 16 over 1. Again, use the toilet seat method. 1 times 1 is 1. 16 times 60 is blah, 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 960, as you can see down here. So we have a sub 1 is equal to 1 over 960. So we have our first term is 1 over 960. Okay, now I just got to put them together and we have our equation. It was a lot of work, but we have our, over here, the common ratio is 2, so that's going to go here. Take it to the x minus 1 power, just what we've been doing with geometric sequence. Then take our first term here and multiply it to get the function rule. F of x is equal to 1 over 960 times 2 to the x minus 1 power. So, what can be cuter than looking at a baby? Looking at a baby monkey. Now, I know some of those notes were kind of tough. Maybe if you need to rewind, watch again. This, again, is posted on YouTube, so you can watch the videos. And now I'll try to do some of the problems that relate to that in the assignment. Good luck. I'll see you guys soon.